The Standard Template Library, or STL, provides us with a wide variety of data structures and algorithms that we can use to write powerful and efficient C++ code. We've seen previously a set of what might be called unitary containers and container adapters that we can use to hold individual elements one by one. In this lecture, we're going to learn about containers that bring two or more types of elements together. And these are called associative containers because they associate two types together. We'll also look at algorithms in the STL, which provide an even more powerful set of standard tools for processing data. Let's look at the simplest of the associative containers, the pair. There are many times that we want a very simple structure that just joins two things together. For instance, you might be keeping track of people and want a person to have an age and a name. The pair provides a quick and easy way of joining two items into one structure. A pair takes two templated types, and the type of the first item and the type of the second item. When there are two or more types needed for a template, they're just separated by commas within the angle brackets. So, to declare our pair of age and name, we'll want an integer and a string. We'll write pair, angle bracket, int, comma, string, angle bracket. And then the name of the pair, which in this case is p. To access the first element of a pair, we just use .first. It will give us direct access to the first element. And the second element is just .second. So, to assign a value to the pair, we can write p.first gets something and p.second gets something. And to access the values in the pair later, we again use first and second. We say cout stream p.second, stream is stream p.first, stream years old, stream endl. Now, we could also just make our own class that combined two specific types. And one advantage of doing that over a pair is that the class name would give an indication of what the intention of the class is. We can get around this a little bit by using what's called a type def. This is just a way of creating a new name for a type. The syntax is to write type def, then the actual type, then the name that we want to use to refer to that type. For instance, if we didn't like using int and we wanted to call these numbers, we could write type def int number. And then we could declare things to be of type number. They'd still be integers. So, in the above case, we could create a new type person that's just a pair of an integer and a string by writing type def pair angle bracket int comma string angle bracket person. This then lets us declare variables of type person, and they'll be integer string pairs. Now, while this lets us have a more descriptive name overall, accessing the member variables is still going to be done with first and second, and there's not an easy way to extend this if we ever decided we wanted some different name. I've also shown one other command available for a pair. The makePair command takes in two arguments, and it returns a pair of those two arguments. It can be a useful way of setting the elements in one statement rather than with two separate assignments. Now, although pairs and the use of first and second are less descriptive than we might like, pairs can be very useful containers when you just want to group two things together without going through the trouble of creating a brand new class for them to exist in. Now, what if we wanted to group more than just two items together? Well, in this case, we can use something called a tuple. A tuple lets us group an arbitrary number of different types of objects together. We just list those types in the angle brackets. We also have a makeTuple command, similar to makePair. However, the downside of a tuple is that we don't have a simple first and second to access individual elements. Instead, there's a function named get that has a really odd form. We have to put the element of the tuple that we want in angle brackets after get. Get 3, get 4, whatever we want. Then in the parentheses afterward, we'll put the tuple name, and that will give us access to that element of the tuple. Let's say that we're running a business where we're letting people buy on credit, and we wanted to keep track of their name, how many purchases they'd made, and how much they owed us. So, in this case, we'd want to create a tuple, storing 3 types: a string for the name, an integer for the number of purchases, and a float or double that can hold decimal values for the amount owed. I've named this tuple type a customer, just to make it a little more descriptive. And then I can use this type customer to declare a variable C. We'll have a makeTuple command, very similar to the makePair command, that we can use to make an instance of that tuple type. So here, the tuple says that John made 3 purchases and owes $100. We can then use a cout statement to access the elements. Now, to access the first element, we write get angle brackets with 0 inside, and then C inside the parentheses, and that'll output John. Get 1C gives us 3 purchases, and get 2C gives us $100. The get function can also assign values to the elements, or manipulate them. Get returns a reference, so we can do anything to the result of get that we would have done to the element. So here, I'm incrementing the second element by indicating 1 more purchase, and increasing the third element by $50. Now that we've seen pairs and tuples, we can discuss the priority queue. The priority queue only takes in 1 type, so it's not associative, but it's often used with associative containers like pairs or tuples. The idea of a priority queue is that we want to be able to insert items into the container and then pull them out in order from greatest to smallest. The values of a priority queue are the priority, or how important that element is. So, each time the element at the front of the queue should be the one with the greatest priority. Each time we pull an element out of the queue, it will be the highest priority item in the container. Now, you might use a priority queue for a task management system. Each task will have some priority of how important it is, so that paying the electric bill might have a high priority, while dusting the shelf might be much lower priority. If you're trying to figure out what task to do next, you'll want the highest priority one. To create an instance of a priority queue, you give a single data type. For the priority queue to work, this data type must have a less than comparison operator defined. This is how elements are compared to find which is largest. If you want to have a priority queue of your own type, make sure that it has less than defined. When using priority queues with a pair or a tuple, the comparison is based on comparing the first element, and then if they're equal, then the second. And for a tuple, this process continues with the remaining elements. Either way, the comparison is already defined, so that you don't have to explicitly create a less than comparison. Pairs are especially common when using priority queues, since we often need to have 2 pieces of information: some value that we're using to determine priority, and then the actual object associated with that value. For instance, say we wanted to have a priority queue where we were pulling people out from oldest to youngest. Well, then we could associate a pair where the first element was age and the second the person. And then the person with the largest age will always get pulled out first. When writing code, elements can be added to the priority queue with a push statement. The highest priority element is accessed using the top function. And the pop function removes the top element. Size gets the size of the priority queue. And empty returns whether it's empty or not. So let's look at an example. A priority queue is contained within the queue library. So notice that I included queue. I use typedef to create a person type that consists of an integer and a string pair. The integer will be the age, the string will be the person's name. I then declare a priority queue of type person. Since the first element of a person is the age, the highest priority element in the queue will be the person with the largest age. And I name the priority queue PQ. Next, I insert 4 different elements into PQ. For each, I call pq.push. And then in the parentheses, I give a person, that is an integer string pair. To create this pair, I use the makePair function, passing in one integer and one string every time I call it. So, overall, I'll insert Jack at age 18, Jill at age 16, Joe at age 19, and Jessica at age 17. Next, I look at the first element in the priority queue. Remember, this is the element that's the largest, so in this case, it's the one with the greatest age. We write pq.top parentheses to get the oldest person in the group. Then, using .second, we get the name of that person. This is what's output. So in this case, Joe, who is 19, is first in the priority queue, so I output Joe. After popping the first element off of the priority queue, that is, after removing Joe, we can again look at the top element. And this time, it's the oldest of the remaining elements, and that's Jack. Priority queues can be extremely useful when we have a large collection, and we just need to be able to pull out the largest element repeatedly without necessarily needing to have everything in order. The next structure that we'll look at is the map, which is a way to associate one value, which we might call a key, with another of any type. Maps come in two varieties, the standard map and the unordered map. And the difference between them is that a map can be iterated through in order from least to greatest, while an unordered map cannot. And generally this means that an unordered map is faster to use. A map uses square brackets to index specific values. Now this is similar to how a vector or an array uses square brackets to access one element of the vector or array. There, the index that you can put in that square bracket runs from 0 up to 1 less than the size of the vector or array. But with a map, we can use almost any value as the index, not just an integer from 0 to something. This index is just the key. So, if we wanted to store the number of bills of different currency denominations, we could use 1, 5, 10, 20, and 100 as our keys. Or we could use a string as the key, so that the indices are cat or dog, for instance. Let's say that we're running an animal shelter, and we want to keep track of how many of each type of animal are in the shelter. We'll use a map for that. Notice that we #include map at the beginning. Now, maps are templated with two types. The first type of the index, and then the type of the value that the index maps to. In this case, we'll want to have an animal name as our index, so the index will be a string. And we're keeping track of how many of each animal there are, so we'll have an integer value stored for each of them. So we declare our map variable, which we call numAnimals, by writing map angle bracket string comma int angle bracket numAnimals. Once we have that, we can assign values to this map. For instance, if we want to note that there are 12 cats in the shelter, we can write the map name numAnimals, followed by the string cat inside of square brackets, and assign the value 12 to that. Likewise, we can assign values for dog and rabbit. In this program, we then ask a user which animal is of interest. We first check the count for that animal. If the count is not 0, then we'll output the value stored as numAnimals by outputting numAnimals sub the string that the person entered. If the count was 0, it means that we have no record for that animal, so we output a short message that the animal is not in the shelter. And so, if we enter an animal that we had data for, like dog, we'll get an output that there are 23 dogs in the shelter. Or if we enter one that doesn't exist, like pig, we'll get a message that it's not in there. Using a map is a good way to group together data. Sometimes you'll hear this structure referred to as a dictionary, since it provides a way to associate an entry, that is the key, with its definition, that's its value. In fact, let's say that you wanted to create a dictionary using the map structure. How would you go about declaring that and then putting an entry in? Here's a solution. We first make sure to #include map. We can then create the dictionary by declaring a map of strings to strings, which in this case I named dictionary. We write map, angle bracket, string, comma, string, angle bracket, dictionary. Once that's done, we can assign elements to dictionary by just assigning a value to whatever indexed value we wish. In this case, I'm assigning a definition for rock, for paper, and for scissors. And I just write dictionary, then in square brackets, the word that I want to define. Then I set that equal to some value. That's all there is to it. Just to illustrate how this works, I've also added a few lines to print out the entire dictionary at the end. So I've created a loop with an iterator named iter that will iterate through the entire map, taking on each value. The iterator will be a pair, giving the key and then the value for the map element. So we can print out iter.first and iter.second to give each word and its definition. Notice that when we run this, all the dictionary elements are there, but they appear in a different order than the order they were assigned. Specifically, they're listed in alphabetical order. This is because I've used a map. If I took this same exact code but replaced map with unordered map, we'd still get the elements printed, but they could be in some totally random order. Maps are a very useful data structure since we often want to associate things with some key value. Keys like this are one of the main reasons you have a unique username or ID number, like your username that you would sign into a website with, coupled with something more specific like a password. And maps come with a variety of predefined member functions that make them even more useful, including @, begin, end, count, and find. Now, in addition to containers, the STL also offers a set of standalone functions that can be called with a wide range of argument types. We say that these are templated functions, since they're not just defined for a single type or set of types, but they can take on a whole range of types. In fact, there are more than 80 of these standalone functions defined in the STL. These templated functions are all contained in the STL algorithms library. So to use any of them, we just #include algorithm. An algorithm can be thought of as a set of steps to follow to handle data or accomplish some other task. So an algorithm is like functions that we've already seen, a set of steps, but it also has a far wider range of applicability. In computing, if a credit card company contacts you about suspicious activity on your credit card, well, they've used an algorithm to analyze the card's pattern of use to decide what is and is not suspicious. Online shopping systems use algorithms to suggest a next purchase based on whatever your recent purchases have been. And computer scientists come up with lots of algorithms to solve all sorts of computational problems. Algorithms describe the critical functionality of most major computer programs, from operating systems to search engines, all the types of programs that C++ tends to be used for. The STL algorithm library contains more than 80 different templated functions, each implementing some algorithm. Templated functions are ones that can take as input parameters a range of various types. So the STL algorithms library functions tend to fall into categories ranging from simple ones like minimum and maximum computation to modifying sequences. Modifying refers to any change at all, including operations ranging from copy and copy backward to move or swap or replace or shuffle. The point of the algorithm library is not to provide functions that we couldn't write on our own, but instead to provide reliable, efficient implementations of very commonly used algorithms that can be applied across a wide variety of data types. Now, we'll talk more about algorithms in the next lecture, but for now, you can think of an algorithm as a set of steps that a generic function will implement to operate. I'll briefly discuss just 3 of the most common templated functions here, but realize that there are dozens more in the STL. One basic function is find. Find takes in three parameters: a starting iterator, an ending iterator, and a value to search for. It returns an iterator, either one pointing to the first occurrence that matches the value being searched for, or if the value is not in the container, then it returns the ending iterator. Here's a short example. Let's say that I have a list of ages of participants in some study, and I want to allow a user to check whether certain ages have participated. Notice that I've pound-included algorithm. In this case, I create a vector of integers named ages with the ages of the participants. Now notice that some ages, like 21 and 22, are repeated. Then I have an infinite loop where I continually ask the user what age to search for. In the loop, I use the find function to try to find the particular age the person entered. I pass in ages.begin, which you recall is an iterator pointing to the beginning of the ages vector, and ages.end, which you'll recall is an iterator pointing to just past the end of the ages vector. The third parameter is the value I'm searching for, in this case the integer that the user entered. Now, find will return an iterator. If the value that the user entered is found, then the iterator will not be pointing to the end iterator. So, I can just verify that the age was found, and for proof, I print the value that the iterator is pointing to. If the value was not found, then the iterator will point to the end iterator. So, I output that the value was not found. Now, this seems like a pretty straightforward function. We could have written this ourselves, just taking the iterator and incrementing it until the match value was found. But the find function, remember, is very generic. Notice that we pass in a starting iterator and an ending iterator. Those could have come from any container that has an iterator. It didn't have to be a vector. It could have been a deck, or a list, or a map. But it couldn't have been a queue or a stack, since those don't have iterators to find. And the container being searched could contain any type. The thing that we're searching for could be an int, or a string, or an object of some user-defined type. Even more, the beginning and ending iterator passed to find didn't have to be the beginning and ending of the vector. We could have searched over any subrange we felt like by passing in iterators pointing to the places where we wanted to stop and start our search. In fact, often find is used to find all values in some container. It always returns the first value it finds in the range. So, a subsequent call could just pass in a beginning iterator that's one increment greater than the last iterator found. This will then find the next instance of the value that we care about. And this could be repeated until the end is reached to find all the values. The code here is an example. We just modified the previous code to always search from findVal forward, where we start findVal at ages.begin, and we have an infinite loop where we output and increment findVal when an instance is found, and we break out of the loop when we reach the end. Find works by searching through the container, just examining every element one by one to see if that value is present. Now, that's pretty inefficient. And unfortunately, if the values aren't in sorted order, there's not much we can do about it. Our only choice is a one-by-one examination. But if the values were in sorted order, we ought to be able to search for them much more efficiently. Let's consider the high-low game, where you're trying to guess a number and are told too high or too low. We had a version of this game earlier in the course. Think about how many guesses you need to guess the final number. After each guess, you cut the number of remaining numbers to guess from in half. And the next guess cuts the remaining space in half again. And mathematically, this means that you need only a logarithmic number of guesses to guess the number, the log base 2 of the total number to choose from. In fact, if you had to guess a number from 1 to 1,000,000, you would only need about 20 guesses. and guessing a number from 1 to a billion would only need about 30 guesses. If we have a sorted list of items, we can use the same principle to search for an element. That would be a whole lot faster than having to look at every single element. So, there's tremendous value in having a list or a vector in sorted order. We can save massive amounts of time by having fewer checks. The STL provides a sort function that will take a container like a vector or list and put it in sorted order. Sort takes in a starting iterator and an ending iterator, and then it sorts everything in between. You don't have to worry about the process of sorting. You can just know that the elements will be sorted. So, just to illustrate, here's a quick example. I have a vector v with several elements in basically random order. For later comparison, I print out the elements of the original vector in order, showing that they are in fact in some unsorted order. Then I sort the vector by calling the sort algorithm, passing in v.begin and v.end as my starting and ending iterators. After that, if I print out the elements of v, I see that they are indeed now in sorted order. Sorting can be useful not only for ordering things in a nice way, but as a way of making subsequent computations faster. So, if you'll be doing several searches for elements, then having the elements in a sorted order lets you use a binary search. STL also provides a binary search function called lower bound, which repeatedly searches over some range by examining the middle and determining whether the thing being looked for is in the upper or the lower half of the range. The code here is an example. It works just like the code that we'd used for find, but we have to first sort the vector. Then we call lower bound just like we called find. Now if the search finds the element, then we get back an iterator pointing to the first occurrence. If it doesn't find the element, then it points to the next largest element that it finds. So in our example, if we search for the value 25, it doesn't find that, but instead it returns that it found a 27, the next largest value in the list. Now for a large list, let's say 1,000,000 elements, binary search with lower bound will be much faster than an iterative search with find. So the upfront cost of sorting the elements one time can easily be outweighed by the time savings on the later searches. Now, based on what you've seen to this point, let's try one more example. Imagine that you want to read in a bunch of people's names and salaries, and then print a list of the people from lowest to highest salary. To read in the information, imagine that you just prompt a user to enter name and salary on the console repeatedly. Since people won't have a negative salary, ask the user to indicate that they're done by entering a sentinel value, such as a negative value for the salary. How might you write this code? Well, here's one solution. We're going to keep a vector of pairs in this case. Each pair will contain a salary followed by a name. And that way, if we have a sorted vector, we'll have the entries in order from smallest to largest. In our program, therefore, we declare a vector, salaries, by writing vector, angle bracket, pair, angle bracket, double, comma, string, angle bracket, space, angle bracket, salaries. We then read in the information from the user, asking for a name and a salary. And we continue this loop until a negative salary is read. In each iteration, we add a new element to the vector by calling makePair to make a pair from the name and salary, and then taking that result as the argument for the pushback on the vector. Notice that when we make the pair, the salary comes first. So, when we sort the vector based on the pairs, it sorts on the salary rather than the name. Remember that pushback adds an element to the end of the vector. Now, once we have all the information from the user, we sort the vector. We just call sort, using the beginning and ending iterator from salaries as arguments. Once that's done, we print out the entire vector. In this case, I've looped through using a for loop, where iter will take on the value of each element. I print out iter.first for the salary, then a space, then iter.second for the person's name. We were able to sort the entire list just by calling the sort function, rather than having to write our own sorting routine. And we could do this because we could compare each of the pairs that we created to determine which of the two elements is smaller. So, now we've seen an overview of everything the STL provides. Besides all the containers we've seen and the iterators that can be used with them, we have implementations of algorithms, dozens of templated functions like the sort, find, and lower bound ones that we saw. Together, these STL containers and algorithmic functions provide support for generic computing across a very wide range of operations. Algorithms are really the key to a lot of programming, and as we deal with challenging problems, we'll want to be able to implement known algorithms and to develop our own. In our next and final lecture, we'll be looking at creating our own algorithm, and it'll be an algorithm to give our computer program some artificial intelligence. I'll see you then.